In the previous video, Aldehydes and Ketones 7 video, we looked at some KEQ values for aldehydes and ketones in nucleophilic addition reactions. And we have some key trends that we wrote at the end of the video. So addition is more favorable for aldehydes than for ketones. Electronegative group near the carbonyl carbon makes addition more favorable. An electron donating group near the carbonyl carbon makes addition less favorable. In this video, we're going to use structures and a diagram to understand why this is the case. So why is this the trend? We can look to resonance to understand. In general, for aldehydes and ketones, we'll use these general R groups. We have a carbonyl carbon, carbonyl oxygen, and we can draw a resonance structure to demonstrate the lack of electron density at the carbonyl carbon. So our resonance, if we resonate pi bond electrons to oxygen, oxygen's more electronegative, so the electrons are closer to the oxygen. The formal resonance structure, we have an open shell carbon now, and a negatively charged oxygen. So these are resonance structures for this molecule. This carbonyl carbon, this molecule in general, is less stable with electron withdrawing R groups. The molecule is less stable with electron withdrawing R groups because the carbonyl carbon is already lacking electrons. We can see that through the resonance structures. So carbonyl carbon's already lacking electrons. If we also have electron withdrawing R groups, we have even less electron density than around the carbonyl carbon. Now the carbonyl carbon, that molecule in general, is more stable if the R groups are electron donating, because now those R groups can provide electron density towards the carbonyl carbon. So more stable with electron donating R groups. And remember, if something is less stable, it is more reactive. If something is more stable, it is less reactive. So we can think about relative reaction rates on a reaction coordinate diagram. Our y-axis is increasing free energy. So G for Gibbs free energy, we'll write that out, or even just standard free energy. And then reaction progress on the x-axis. And we'll compare if we have, let's use this pink color for electron withdrawing R groups, and then we'll use blue for electron donating R groups. So if we have electron withdrawing R groups, then our starting material, the aldehyde or ketone, will start at a higher energy. So starting material with electron withdrawing groups, then the starting material will do kind of two. Actually, let's just go ahead and split this into two reaction coordinate diagrams. So we'll do one for electron withdrawing and one for electron donating. So G for standard energy, same thing as standard free energy on the first diagram. So if we're starting our we have our starting material at this relative energy. If it has an electron withdrawing group, then the starting material with an electron donating group is more stable, so it would exist at a lower energy than the starting material with electron withdrawing group. Now our intermediate, the charged intermediate, is about the same energy for both. So we'll put these, the transition state, at the same energy. And the products will be at about the same energy as well. So if we draw out the reaction coordinate diagram, we have our transition state at this energy, and then products at a lower energy for both the molecule with electron withdrawing groups and the molecule with electron donating groups. So we have our two diagrams to show relative reaction rates. Our pink diagram has starting material with electron withdrawing groups. Blue has starting material with electron donating groups. Now remember, the reaction rate for a reaction depends on the activation energy going from the starting material to the transition state. A lower activation energy would result in a faster reaction. While when we have a molecule with electron withdrawing groups, its activation energy in total is much lower than having starting material with electron donating groups, because the starting material with electron withdrawing groups already exists at a higher energy. So having a lower activation energy results in a faster reaction. We have a more reactive starting material, and that's why the KEQ for these reactions are higher if we have an electron withdrawing group. The reaction will happen quicker. So the difference, let's use this right here. So this difference between starting material energy, I'll use another color, here's a note. So difference in starting material stability is equal to the difference in this activation energy. So more reactive starting material, faster reaction will lie to the right.